Hey everyone, and welcome back to another episode of the Delphi Intelligence podcast. Today, I'm delighted to introduce you all to Philip, the founder of Starcloud. Philip, thank you for joining us. I got to say, reading your white paper this summer, on my honeymoon, in fact, is probably the most energizing thing I've read in a long time. I'm extremely excited to chat to you and learn a little more. Maybe you could start with just a little bit of an intro and kind of explain what you guys are up to.
For sure. Firstly, thanks so much for having me, and apologies to your wife for ruining your honeymoon. We're building data centers in space in order to be able to take advantage of the abundant energy in space and the ability to scale almost indefinitely. So we're launching a demonstrator satellite in November this year, November 2nd, which will be about 100 times more powerful GPU compute than has been to space before. So we're launching the first H100 from NVIDIA. And then next year we've got our second launch, which will be at least 10 times the first one in terms of power output. And then we basically scale up from there. Happy to talk more about the long-term vision or other things, but yeah, I'll stop there.
Yeah, we'll jump into it. I guess before we do, I'd love to understand, what the hell? Seemingly only a madman would go after something like this. Like, what shaped your sort of instinct to go after space, to go after such a crazy idea of, shifting heavy compute off-world?
It's a good question. Well, my background, I started my career as an engineer, spent the first 5 years on the engineering side. I studied applied math and theoretical physics, undergrad and masters. And then I moved over to the commercial side. So I was with McKinsey for a few years, working with the space agencies of various governments. That's where I started to notice that the launch cost was very rapidly falling. So it used to be about $60,000 a kilo with the shuttle program. And then with Falcon 9 and Falcon Heavy, it came down to less than $10,000 a kilo. And what's really interesting is where it's going, which is that with the Starship program, it's going to be potentially in the hundreds of dollars per kilo, but certainly less than 1,000. And the reason for that is it's the first ever fully reusable rocket. I started looking at a bunch of different things. Actually, I went down to Starbase, Texas, where they're building that program in 2023. And that was before even the first launch, just to have a look around, just like as a tourist. And what struck me there is the capacity they're building for is absolutely gargantuan. So they're building these two massive Starship gigafactories, one in Florida, one in South Texas. They're basically Tesla production lines, Tesla gigafactories for Starships. So they're designed to produce in 18 months 3 Starships a week, and in 36 months 3 Starships a day, which is just mind-blowing capacity when you consider that compounds on itself. So if you build a new Falcon 9 every day for a year, at the end of the year you have 1 Falcon 9. If you build a new Starship every day for a year, because it's reusable, at the end of the year you have 365 Starships. So not only does it have 5 times the payload bay capacity of Falcon 9, but it also compounds. So we might see 1,000x increase over the next few years in launch capacity with a 10 to 100x decrease in cost. So anyway, that got me thinking about what kind of business models have we been wanting to try for ages that we couldn't. I've been a sci-fi kid since a sci-fi nerd since I was a kid. One of those is space-based solar. And so my co-founder Ezra and I started discussing what would the launch price need to be for space-based solar to work. That's basically a concept where you have huge solar panels in space and you beam that power down somehow. The problem with it is you have a 95% efficiency loss getting power from space to Earth. So we came to a number around $50 a kilo, which is within the range of Starship, and actually that's what we started looking at. And then we were like, well, most new energy projects terrestrially are being built for data centers. So what would the launch cost need to be if instead we had a cheap way to get the data center to space so we don't lose that 20x in power sending it down? And we reran those numbers and came to a number around sort of $500 a kilo number. And that's where the white paper came from. So that became then the basis of a white paper. And then from there, we got off to the races.
Very cool. It makes a ton of sense. When I heard on another interview you talking about that, if you look at the composition of humanity's energy consumption, all the forecasts, right, it is all compute. So it kind of makes a ton of sense if you can shift it out there. You make it sound so casual, the journey into going after something so crazy. I read or heard somewhere as well, like I'm curious. You mentioned, I think, that you're one of five brothers. I thought I'd flag it because I also am. So
Oh, really? No way.
yeah,
Okay.
it jumped out to me. It's quite a rare thing.
Where are you in the stack?
I'm the second eldest. So yeah, three are still in production, and one's fully operational, let's say. But yeah, I'm curious, like, what the hell are like all the brothers doing? Like, did you guys all grow up with this sort of interest in sci-fi? Is this a shared thing? Because certainly it's something I share with my brothers. So I was curious about that piece as well.
Only really with my identical twin brother. So we're the youngest of the five, and I'm the youngest of the youngest.
Right.
So yeah, we competed quite fiercely in, high school and university and things. Basically, have identical career paths actually. But no, my other brothers didn't really. I mean, two of them didn't really go to university. One dropped out of school when he was 16 and became a chef. One he manages a kitchen at a golf club now. One like became a barman, like manages a bar, and then now does something else, but not anyway.
I see. Not shooting
Like,
data centers into space.
no, yeah.
Nice, nice. No, always curious. So yeah, I guess I want to then ask, like, where the hell do you even begin after going? You mentioned, with your co-founder, you guys are like, damn, this might actually be a sort of viable path. Like, where do you even begin in sourcing the engineering talent and convincing them that this is a viable path, and also that you're the guys to helm the ship and help execute the commercial side and put everything together?
Yeah, that is a great question. So we initially thought to get great space talent, we need to be in El Segundo in LA. So that's where we initially put the company. And then it turned out everybody we wanted to hire was in Redmond, Washington, which is where we are now. And the reason for that is Starlink is here, and Starlink produces, I think 90% of all satellites launched in the last few years were designed and built in Redmond at the Starlink facility. So if you any role you can think of, so LA is good for launch, propulsion, aerodynamics, anything that's like spacecraft thermal engineer or anything like that, you're going to find much more of up here where we are. So we basically then relocated to here. My third co-founder, Adi, was previously at SpaceX, so that definitely helped, convincing some SpaceX folks to join. And also 20 years at Microsoft on the data center side, so we got some kick-ass engineers from Microsoft through him. But yeah, I mean, I think if so we raised a bit of cash as well, and we didn't hire until we'd done a $21 million seed. So, once you've got a bit of cash, you've got credible technical co-founders. Ezra, has a PhD in engineering and designed the NASA Lunar Pathfinder deployables. Wow. Then I think people are interested in the mission. So I think it's actually, once you've got a few, it's not as difficult as you might imagine.
Interesting. Yeah, I guess the intrigue, the mission's exciting enough that kind of makes sense, right? And no wonder people want to work on it. So, yeah, I'm curious then, in terms of like, all right, you assemble the Avengers, so to speak, bring some sort of cracked engineers together. Like, maybe you can tell us like a crazy fucking story from the early idea validation, right? Like, where does one even begin? Like, what were the first sort of engineering pieces? Like, what were the crazy early learnings?
Yeah. Well, I mean, we went through Y Combinator last summer, so we were not in the workshop, and we were down in San Francisco. So, like, Ezra was like, you have these like goals every 2 weeks with the group. I think one of those goals was Ezra had to prove that a deployable, like a mechanism for deploying the solar panel, could be done, and so he ended up like making that mechanism in our living room in our house next to the YC office.
Nice.
But no, yeah, I mean, we tried a whole bunch of different stuff. Particularly, so we are not doing, for the first satellite, we are not doing the satellite bus. That's just an off-the-shelf manufacturer. There's about 50 different providers of that. We don't need to reinvent the wheel on things like reaction wheels and, propulsion we did do actually, but torque rods, like all of the different spacecraft control mechanisms, we don't really need to reinvent the wheel on. So the bit that we're doing for the first spacecraft is the compute module, the antennas, and thermal management system, basically. So that constrains what we need to test and try somewhat. It's not like we're building a whole satellite from scratch. So yeah, in terms of the different thermal management solutions, we tried every different. We've got basically this liquid immersion cooled system, and so for that, through every different formula of potential thermal fluids that we could use to keep that cool. right now we're putting an H100 in a cyclotron, which is basically a high velocity proton beam, shooting protons at it at 20,000 kilometers a second to find out where it fails. Because I think we might now be the only people in the world that know where an H100 fails if you shoot protons at it at a very high speed.
I love that. I mean, I guess we didn't really touch on like the stuff that you guys described in the white paper, right? Is building this 5 gigawatt data center, right? A 4x4 solar array, a 4x4 kilometer solar array, and like I think it was a 1x4 kilometer radiator, like this colossal thing, right? And so, I guess that leads me to one of my questions. Like, yeah, I think in order to do something that big, it needs to be, well, something about your orbital paths, which we'll get into, right? You need to go basically much higher up into this radiation belt, right? And so that's like the first major engineering challenge, right? Is the radiation shielding piece. Like, yeah, maybe you can tell us just a bit more about that. Like, I guess firstly, like you've said elsewhere that it's like half the engineering time is dedicated on radiation shielding and the other half is on like heat dissipation, right? So maybe you can just talk us through these two big like challenges and how you're approaching each and what the key like variables you're trying to solve for right now are.
Yeah, for sure. So with the radiation shielding, there's 3 levers you can pull. So one is shielding, another is software, like mitigating the effects through software, and the last is choosing where you fly, choosing the orbital path. And so, yeah, for shielding, that's just a lot of testing with different materials and other things down in the cyclotron, and other ways of testing. For software, my co-founder, or sorry, one of our first engineers was doing IoT stuff for Microsoft for ages, and so he has a whole bunch of experience in writing redundant software, so that if you have a bit flip, you can have voting algorithms and things to know where that's happened. And then the last one is choosing the orbital path. So for the first few satellites, we'll be flying in what's called a VLEO orbit, so very low Earth orbit. That's around 350 kilometers altitude. So it's about 100 times less radiation there than there is where, Starlink and others fly at 500 kilometers altitude. So we're pretty okay for the first mission. For the second mission, we're at 600, and then for later missions, as you mentioned, we'll need to be much higher. And the reason we'll be higher in the later missions is if you don't ever want to go behind Earth's shadow, the lowest you can fly is around 1,300 kilometers. So yeah, then you really are in quite a nasty high radiation environment. I mean, the nice thing about being there also is nobody else wants to fly there, so you don't have to worry too much about orbital maneuvering and things. But what's good about flying there is once the satellite's larger, the compute volume is scaling the compute scales with the volume of the satellite, whereas the shielding scales with the surface area. And so you have a natural tendency that when the satellite gets larger, the mass of shielding trends towards 0 as a percent.
Interesting. Yeah, and I assume that's a pretty big burden on smaller payloads, right? Like the amount, as in like the shielding occupies a significant amount of the mass going up there.
Yes.
No, it's super cool. I was also reading around like, yeah, the orbital path, right? Like what do you call it? A dawn-dusk sun synchronous orbital path up there. Like, super cool, right? I like one of my questions was, I know space is huge, and anyone that does anything with space says you don't really know the extent of just how big it is. But like, assuming these multi-gigawatt things, let's say 10 years out, 15 years out, like, can you really stack tons of these 4x4 kilometer arrays up there? Like, yeah, just tell us a bit more about that.
Yeah, do you mean in terms of orbital collisions and things like that?
Yeah, exactly.
Yeah. So space definitely is huge. We do need to be very careful and make sure that we're a responsible user of space. So yeah, one of those we can do that is flying up in that higher altitude. I would say, I think the probability of the Kessler syndrome in people's mind is often somewhat larger than it actually is in reality. Kessler syndrome, for the listeners who might not know, is where there's a concern that if you had one satellite collision, that would create a debris field of millions of small fragments of satellite, which would then, or could then, collide with other satellites and create more debris, and then that would collide with other satellites and create more debris, and then you would just end up with this sort of like dust of like fragments in low Earth orbit, and that could make Earth, low Earth orbit unusable. There's a few reasons why that is much less likely than people imagine, especially at the lower altitudes, anything below about 500 kilometers. One is, for every orbit you go around, your altitude lowers quite significantly if you don't have propulsion. So hundreds of meters at least, and because of low levels of drag from the upper atmosphere, and so the chance that you hit something on the second pass is like very low, and you might think, okay, that's all very well to say, but like, what's the evidence of this? And one interesting piece of evidence is in the 1970s, the US government ran this experiment to put 400 million tiny needles about this big into low Earth orbit, and they put them at about 3,000 kilometers altitude, which is in theory a terrible place to drop them off because there's hardly any drag from the atmosphere there.
It's like harder to deorbit, right? It would take a long time.
Yeah. Yeah. So, and as I understand, at least 5 nines of those are down. So like 99.9999 are down %. And so I think probably only, basically the entire, the chance of hitting any one of those is basically 0. And the reason they deorbit is because you have this 3-body problem with, so you have pressure from the sun in terms of both radiation and actual photon pressure. Then you have this Earth Moon system, and if any time anything comes slightly close to the atmosphere, it's just a matter of time. Then it's like a year or two before it's going to be down, because once it passes within a few hundred kilometers or within say 600 kilometers of the Earth, that's going to start creating drag that will just spiral it in. So yeah, I think it's reasonably unlikely we'll have some Kessler syndrome effect. But yeah, where we're flying out at 1,500 kilometers, I think it's we can put many of them before we start having problems with that.
Well, let's hope none of those remaining 0.001% of needles come flying through anytime soon.
Yeah.
I am intrigued though. Like I've been reading about like the sophistication of a lot of the orbital debris tracking. They're starting to put ones to actually go and orbit, in the outer atmosphere. Like, I guess the crazy shit is just that some of these things are orbiting at like almost 20,000 miles an hour, right? It's like the collisions, if they were to happen, are crazy. But sounds like you guys are sort of beyond that. I wanted to also ask then, like, obviously radiation shielding, like big challenge. Sounds like you guys have unlocked a lot of proprietary data by using whatever that device was called. One of my favorite things I've read about with space is this Carrington event that happened in like the late 18th century. Yes. This massive solar flare that set telegraphs on fire, right? Like, I mean, what degree of how many standard deviations of your expected like CMEs and solar activity do you need to account for? Because obviously, if you're shifting a multi-billion-dollar data center or whatever it ends up being into outer orbit, like this is a huge thing to consider.
There's 2 ways to answer that. So one is, yes, it's pretty unlikely, but it's not impossible, obviously, because of the Carrington event. The other is, a lot of our satellites would be a little bit fried if the Carrington event happened, but so would most data centers on Earth.
Right.
So unless you're planning on building concrete around all the data centers on Earth, we have the exact same risk profile. So, yeah, I mean, at some point, we can do certain things, like we can shift coolant from the radiators in front of the solar panels. We can reorientate the spacecraft so that it's, instead of flat on like this, it's angled on like this. And I think what it will really require some kind of early warning, and the type of early warning that would be useful would be a probe out in the first Lagrange point between the Earth and the Sun that could give us 10 minutes warning at least. For now, it's not ideal, to be honest.
I mean, I'd seen that like they have some tracking systems in place, like where they supposedly, if you could get 24 hours, they could shut off data centers on Earth and the energy grid and whatever. But anyway, I wanted to ask because I'm curious for these like freak events that we do know what happens. Like, I'm fully bought into this thesis of orbital compute now, and I'm just curious on that front. But let's see. And then I guess the heat dissipation was the other one I wanted to ask and understand a bit better. Like, what the hell does radiating 5 gigawatts of energy look like?
So I mean, it's a huge challenge. That's definitely where the most of our engineering time goes. So the rough calculation is 1 square meter of solar panel in space produces 800 watts per square meter. Sorry, 200 watts per square meter on the solar panel side, and the radiator, if you keep it at 25 degrees, will dissipate around 800 watts per square meter, which means we need about a quarter again the size of the solar panel in radiator. So if your radiator is 4 kilometers squared, you need a 1 kilometer square radiator to dissipate that amount of heat. And so that is the core of the IP we're developing, is very large, easy to manufacture, low cost, low mass deployable radiators. Yeah,
Interesting.
we have some interesting designs there.
And then I'm also just curious, like with that level of emissions, like if you do start scaling up to that, is there not like force exerted in space, like on the actual spacecraft, right? Do you have propulsion on the other side to net it out, or is it not big enough even at that scale?
We'll have some station keeping to net it out. Yeah.
Interesting. Super cool. And then I guess one of the other things I wanted to ask around is just like the data uplink, downlink. Like, I mean, I assume you're not going to be doing like full training runs or whatever in space. It'll be primary inference based stuff for like AI workloads. But like, is that a primary constraint, or is it very easily solved? Just bringing up enough data either by lasers or I don't know. Would love to learn about that.
My co-founder is very passionate about the idea of a data shuttle, like a little module that we can send up and dock in and dock out. No, I mean, we potentially will be doing training runs at some point, but you're right, not for the foreseeable future. And the way that we ship data around is just through Starlink. So Starlink has extremely high inter-satellite connectivity data rates. So I think each satellite, and I think this is public, is each laser they have is 400 gigabit a second data rate, which is more than most data centers have as their, or more than many data centers have as their in and out pipe. So, and you can have multiple lasers, so you can have much more than that if you want.
Very cool. I saw also that they're adding, with the new V3s going up next year, they're adding like 4,500 terabytes a second or something of like capacity for the like terrestrial network. So I assume it sounds like it's solvable by that. Interesting. I also wanted to just touch on like, what are some of the more like attractive properties of space broadly, right? There's the scale of it. Obviously there's like solar potency, right? Like outside the atmosphere, you can harvest a lot more energy. I think one of the things that you've touched on elsewhere that I thought was really interesting is just like, if we are heading towards Kardashev type 1 or whatever, and we do 100 to 1,000x, like our compute usage on Earth, like the heat dissipation alone on Earth would fuck the planet. And that was a really interesting thought that I hadn't come across before. Maybe you could just tell us more about, that piece.
Yeah, exactly.
Yeah,
exactly. People often talk about global warming from the context of carbon emissions and the extra heat that they trap. And you're talking on the order of a few degrees of warming expected through that effect. And that is a potential threat that we should definitely mitigate. The bigger threat coming down the line is if you have, as you mentioned, on the order of sort of 10 to 100 times the current data center capacity, even if all of the current energy use becomes carbon neutral somehow, so even if it's fusion or solar or something else, you're literally just pumping enormous amounts of waste heat into the atmosphere in terms of boiling off fresh water, which is how current data centers keep keeping cool. So at some point we will need to get compute off Earth. And 10 to 100 times is certainly, 10 times is certainly within our lifetime. So it's certainly worth thinking about now, I think. I think the other big advantage of space, which is often overlooked, is the sort of permitting cycles are much quicker than they are on Earth. So if you want to build a new nuclear project on Earth, you're looking at sort of 5 to 10 year, even longer sometimes, lead time on permitting. Whereas we can launch a 40 megawatt data center in a week. It's sort of first come first serve on orbital planes.
That is surprising to me that the regulatory muscle memory has got to a point where you can actually run these processes like relatively headache free. Is that likely to remain the case? As if Starship's truest vision manifests over the next 10 years, there's going to be so much shit going up there. It's going to be like trivially, cheap, whatever, to send stuff to orbit. So will that remain the case? Do you anticipate that getting harder? Is it a question of building these relationships now and you guys there's some defensibility in that long term?
Yeah, it certainly will require a lot of collaboration with the FCC, and I presume that there will be more regulation coming down the line as Starship comes online and more people want to put more stuff up. But for now, it seems the one interesting potential of this business model is in the same way that people who bought Spectrum 20 years ago are now making a killing off it. I don't know if you saw, just EchoStar just made an absolute fortune selling Spectrum to SpaceX. There's one interesting idea, which is that once you have a satellite in an orbit, that's basically then until it deorbits or until something, unless you let it go, that's basically then your orbit. And certain orbits are quite valuable, particularly this dawn-dusk sun synchronous orbit. So there's an argument to be made that even just by getting there first, we're building some kind of value.
That's a really cool idea. I guess that was what I was asking earlier, right? Like how scarce is that, whatever, that 1,200, 1,300 kilometer range? It's really cool. It's an interesting point. Nice. It's like a cooler version of domain sniping sitting on these orbital paths, right? Like, I like it a lot. Very cool. Okay, so I wanted to switch gears a bit and talk through like I guess the business model. So like your ultimate model, am I right in thinking it's just like selling compute time to hyperscalers like in the long term?
Yes.
Okay. And so
Or
like,
actually, we'd rather be thought of as an energy provider in the long term. We don't necessarily want to have to buy tens of billions of dollars worth of chips. So in the end state, we would rather we provide a box that has Earth-like conditions in terms of atmosphere and power and cooling and networking. And then people can do whatever they want with that box. If they want to run compute in there, that's great. If they want to do manufacturing in there, that's great. Or, whatever they want to do. So in the end state, we can be thought of as a provider of power, cooling, and connectivity, and then everybody can do what they want with that.
very cool. And then I guess want to talk through like the roadmap from here, right? You've mentioned that there's this like November 2nd launch, like what exactly are you guys validating with that? These H100s in space, the most compute by 100x, I think you said in space ever. Like, let's talk us through a bit what the next like 12, 24, 36 months look like in terms of roadmap.
Yeah, sure. So most powerful GPU compute by 100x. Then the first thing to demonstrate will be the first to train a model in space, the first to do high-powered inference in space, the first to do fine-tuning of a model in space. We'll be running a version of Gemini on that satellite in collaboration with Google Cloud. So there'll be a whole bunch of firsts, which will be very interesting. Then next year we're launching with the Blackwell architecture. That's going to be a sort of close to 10 kilowatt satellite, which is massive for a commercial satellite. We'll have by far the largest commercial radiator in space. And that one will be the first to provide a proper service for customers. The first one will test out what customer workloads, but the second one, we'll have proper contracts with people who rely on the service. So mainly with DoD customers initially, but also with some Earth observation and sensing companies.
That's one piece. So like these early revenues are going to largely be like, third-party contracts, both commercial and defense, as you say. I guess for both, there's a lot of like data sensitivity, whatever you're doing, that like edge compute off-world for, like, how do you do the sort of containerization and navigate all of those pieces? It's quite an interesting one as well. Just the logistics of that.
Yeah, no, it's very interesting. So we've got the guy from Azure who is doing GovCloud security. So that's basically where we can both physically and in software segregate. So we'll have a whole bunch of GPUs on the second satellite. We can have physical barriers between. We can say, okay, these two GPUs are for a certain DoD customer and they don't have any software link, or they don't have any networking link with the rest of the satellite. But also just in virtually we can segregate for different customers who are less sensitive on the security side. But everything is end-to-end encrypted, and it'll be as secure as sending data through Starlink.
Very cool. And then, so assuming these work, you start scaling the early revenues, you're building, slowly launching bigger and bigger satellites. I think I'd read somewhere that you said like Starship at 100-ton payloads will equal like roughly 40 megawatts of compute. And you guys are building this big solar array in like a modular spine, right? So you can basically send them up and assemble them over time. Like at what point does the construction of that phase start, right? Like going for a big gigawatt, sensor basically.
So not until we're launching full Starship payload bays would it make sense to hook them up modularly, because we don't really need to. We can just launch bigger and bigger payloads. My expectation is we'll probably have like on the order of a few hundred up before we even start hooking them together. Because if you're only doing inference, there's no reason to hook them together. You can just use these optical links to connect them. And so in that instance, and until we start having lots and lots of these things that we would want to train a model on, and I'm to train a model in 5 years' time, I'd imagine will be on the order of several gigawatts. And so that's, yeah, you're looking at about 100 of these modules. So yeah, until we have a few hundred up, I expect probably not gonna. And that's like in the early 2030s, so that we'll have the first full Starship payload bay up.
Yeah, this is one thing I want to just double click on. I mean, I know you probably have access to privileged information around this, but I guess like without asking for any specifics per se, like I see wildly varying forecasts for like what timeline or where it's even going to get to, right? Is it going to be $200 a kilo, 100 or 50 or 10? Some people, the gigabulls say like, like obviously a lot of your thesis in terms of like the fullest fruition of it is dependent on, I don't know, there's probably a break-even point, right, at like a couple $100. I don't know. Like how confident are you in those like forecasts? How aggressive are you like personally based on all of your experience assessing this stuff?
Yeah, anything below 200 is perfect for us. I don't think in my financial model, we've not got anything below 300, and that starts around mid-2030s. It starts to fall around, we're break even around, between around $500 a kilo mark on the competing with terrestrial on energy market. If for some reason it's delayed, we'll just run the business for other satellites. So we're building a business that is profitable with the Falcon 9 launch cost, serving other satellites for now. And then, if that launch cost is delayed in coming down, then we'll just run that smaller business. And when it's ready, then we can start scaling up.
Very cool. And I'm curious, like, if assuming it does drag, should it drag? What are some of the other cool, like, wacky ideas you guys have toyed around with, like, beyond just like, whatever, like EO stuff, like defense stuff? I heard in one interview you did that you was saying, joking perhaps about shifting like Bitcoin mining off world, doing key storage and stuff like that. Like, I mean,
that's going to happen next year, by the way. Like, Bitcoin mining is a great way to use energy when it's not being. It's very similar to the Crusoe model actually, where they have these huge mining rigs that they would stick, 10% of that capacity they'll put in very high powered GPUs, and because the utilization on those is much lower than the utilization that you can get from Bitcoin mining rigs. So because you can basically get close to 100%, it's only the failure rate on the chips. It's not a demand. Whereas for high powered GPUs, there's only so much demand at certain times of the day and whatever. So yeah, we'll have some mining rigs on the second satellite.
That would be so sick. I love that idea. It makes a lot of sense. We put a report out a few years ago, pre crazy AI boom, and like at that point our estimates were showing that 20% of the energy footprint of the internet was already BTC, right? Like that's another big energy demand. So that's a really cool vision. I like the sound of that. I look forward to that day. I guess like I'd also love to just hear from you what some of the other less obvious challenges about space, about either like specifically technically what you're doing or just broadly operating in space, a space startup, like what maybe wasn't obvious to you at the outset that now is.
I think what surprised me at the very beginning of this was just how bad connectivity is in space. So you have to, for most satellites, you have to wait half an hour or between anywhere from 30 to 90 minutes before you get to a ground station or till you're flying above a ground station. And then you only have about 5-minute window where you can downlink as much data as you can, and you're getting, less than a gigabit a second data rate, most of the time a few hundred megs. And so, yeah, like I had sort of fairly naively just presumed that space was similar to ground in that there was connectivity and it was a bit like the internet and you see a Wi-Fi or something. But and that does exist to a degree with some of the other constellations like Tidris and Iridium. But if you want cheap, fast connectivity for a LEO satellite, that's very constrained. And that's one of the main reasons now why people are interested in using our compute, so that they don't have to, they can run all this high-powered inference in space rather than having downlink.
See, that's one thing that strikes me as strange, the notion that it's more likely sooner going to be economically feasible to put compute off-world and run it on the edge, like edge compute, than just fix downlink. Like, surely all of what Starlink's been doing, like, that's surprising to me. But yeah, let's see how that side evolves. And then also, like, I mean, you mentioned you're doing some defense stuff, which obviously you won't be able to share too much on, but like, I've been reading a lot about just the, geopolitical side of space and this very sort of like China, Russia, and then US led sphere of like space regulation, even the like lunar programs that are ongoing. Like, yeah. I mean, I've been reading about like Chinese debris removal satellites wiping out other communication satellites accidentally. Like, is any of this weird shit that's going on a concern for you or your customers? Like, if you're putting material amounts of chips and heavy infrastructure off world, like, yeah, how often do you guys run into this conversation?
Yeah, I mean, yeah, it's certainly something to be cognizant of. There's a few aspects to it. So one is that all any offensive action in space is very visible. So anything that's above a centimeter cubed in space can be tracked and is tracked on the ground. So if there was to be any offensive action by Chinese satellites against our own, we would definitely know about that, and that would be considered, certainly a destruction of satellite would be considered an act of war. So, there's treaties in place to govern what would happen in that instance. So yeah, both the US and the Chinese are building offensive satellites or spacecraft that can intercept and can take actions. I think we're fairly dependent on the US Space Force to keep us safe in that regard.
Nice, cool. It's interesting.
I would say if you're going to blow up a data center in space, you could also blow up a data center on Earth. I mean, it's a lot easier to send a missile at a data center in Virginia than it is to send one in space. Maybe there's different optics around that, but
No, absolutely. It's just it's interesting to me that that's a source of friction geopolitically now that they're starting to position for all of this stuff. I couldn't actually believe it when the US Space Force was announced all those years ago. I was like, feels very, very sci-fi, right? But yeah. I'm also curious then, like, I don't know, like you mentioned you grew up reading a lot of sci-fi. Obviously, I mean, I kind of touched on the Kardashev type stuff, right? Like if we can start harvesting planetary energy using all this compute, like what are some of the ideas that really blow your mind around this? Like around like where this stepping stone that you're building, like validating this as a direction of travel, like what's the crazy shit that excites you about where we might go, say, like within this century? Yeah.
Within the century, I'm very certain we'll have started sending spacecraft to the nearest star, to Alpha Centauri. It will take quite a long time to get there initially, on the orders of tens of thousands of years, but it's definitely something we should start doing soon, I think. I think it would take on the order of 5 to 10,000 years to build a proper full Dyson sphere, or Matryoshka brain, which is a Dyson sphere hooked up to shitloads of so what we're doing, I think, will prove that it's there's once we've built these big radiators, it's going to be obvious to everybody that this is where compute lives. And then to start validating the Dyson sphere idea, you would start putting them in a sun orbit rather than in an Earth orbit, because at some point we certainly will run out of space in Earth's orbit. So for less time-sensitive workloads, you could definitely put bigger structures in the Lagrange points. The first, you'd probably want them in any of the four Lagrange points. Probably not the second, but yeah.
Right. That's super interesting. I mean, as you said, the Matryoshka brains was an idea that I thought was so wild, right? Like, for the same reasons that you concluded that compute and not just solar energy harvesting is the way to go. Like, I don't know why we'd send a Dyson swarm, right? To like, how do you transmit that energy, basically? So I love the idea of putting massive arrays of compute, orbiting the sun. It will be so cool. It'll be a cool day when that comes.
It's gonna happen.
Either
that's going to happen, or we're going to wipe ourselves out. And I think it's probably more likely that we wipe ourselves out, given the implications of the Fermi Paradox. But we'll see.
Totally. I love, the Fermi Paradox, Bostrom's great filter, all this kind of stuff. I feel like we're gonna unlock incredible insights into both of those like theories, I think, in the next couple 100 years. On that point, you guys are facilitating AI, the ultimate goal of it, AGI, summoning digital God. Like, how do you rationalize all of that? How do you feel about it? It's both equally, exciting and terrifying. Like, how do you think about all that stuff?
It is very terrifying. I try not to call it summoning digital God, but there is a sense in which it is that. I think I am extremely concerned about the idea that, like, a swarm of the killer AI drones would make mincemeat of basically the entire planet within a very short period of time. And that is what we're planning on building, it looks like, both the US and the Chinese. And if those two things go to war, we are very screwed. And as I say, my working hypothesis is that is at the moment the most likely outcome, because if that wasn't the most likely outcome, or it could be anything, but like it seems to me that intelligent life is very short-lived in our galaxy, at least, because it would be extremely simple to colonize the galaxy. Like you could do it in like a few million years, and that's sort of the blink of an eye in evolutionary and galactic timeframes. So it implies to me that there hasn't been very sophisticated intelligent life anywhere in the galaxy before that survived more than a few million years. And so then, yeah, the question is, why did it not survive more than a few million years? And I think AI being self-destructive is a very plausible explanation for that.
Well, chin up, I suppose. Onwards. Let's hope it's not the case.
Too much you can do about it. I mean, yeah, the alternative is we are really the first, and we are really exceptionally rare, and maybe that is the case. And yeah, I don't have a huge amount of evidence either way. So
there's a quote that I always love by a physicist, I forget his name, who said that there exist two possibilities in the universe: either we're alone or we're not, and both equally terrifying.
yeah,
And I think that's so true. Like the responsibility, the weight, if we are the only. But anyway, let's see. Let's hope sense prevails and we figure out our current qualms. But anyway, I'm curious. So less abstract sci-fi visionary terms, having immersed yourself in the space industry and as a space enthusiast, what is some of the other shit that's happening in the next 10, 20 years that's really exciting you? Like I kind of touched on, like, I didn't know that both the US and China have lunar programs. They want a permanent human lunar base in the next 10 years. Like, what's the stuff that's really exciting you about where this industry is going?
By far the most exciting is the permanent base on Mars. So that's the whole ambition of SpaceX. And given that SpaceX is heading to be by far the most valuable company in the world, that seems like they have the resources to do it. So I would not surprise me if within the next 20 or 30 years we see large cities being built on Mars, or a large city that's self-sustaining being built on Mars. I mean, it won't be self-sustaining in 20 or 30 years, but there will be maybe hundreds of thousands or thousands of people on Mars in that time frame, which I think is just mega exciting. Other things are asteroid mining is going to be a big business within a few decades. Once we have lower launch costs, asteroid mining is going to be huge. I think tourism will be interesting, particularly closer to home. Lunar hotels and LEO hotels, I think, will be a big business too. I would definitely love to go to a lunar hotel. I would pay any amount of money to go to a lunar hotel.
As would I. It's always been my great dream to take my father to space. He loves space, but having looked into it, I mean, it still seems to suggest it's going to be like 20 mil a seat for the foreseeable future. Maybe, I don't know. Let's see. Hopefully that changes.
Hopefully that changes with Starship, but yeah, let's see.
Yeah, there we go. And then I guess, yeah, so a bit like a bit closer to home, like if all of your forecasts are hit, like what does Starcloud look like in 2035, 10 years out?
It could be the case that in 10 years' time, most new data centers are being built in space, purely because of the constraints we're facing on energy terrestrially. So in 2035, that's enough time to build out the supply chain for Starship and the volume production of Starship. And I think by that point, we'll have proved that we are much more cost effective than building data centers terrestrially. So yeah, it might not be that we're the only player in town, and I imagine there'll be some others, even some of the large players could enter. But yeah, it would not surprise me if we start seeing most new data centers being built in space. That still means probably 99% of all data centers at that point are still terrestrial, just because of this massive build out that we're doing right now. Yeah.
Yeah, sorry, it was a little loud there. I wasn't sure what was going on there.
One of our engineers arrived on a motorbike.
Right, nice. Cool. No, that would be exciting to see. I mean, if you had to guess based on all of your explorations so far, like who would those other people competing be? I mean, obviously, like Elon, SpaceX, XAI, right? You're curious who else you have an eye on.
I mean, AWS has Kuiper. I think that would make quite some sense as well. All of the other hyperscalers would need this capability. None of them currently have space arms, so Microsoft doesn't, Oracle doesn't, OpenAI doesn't, Meta doesn't, Google doesn't. So that's where I would expect they would want to partner with somebody with that capability, like us. I don't see Microsoft using XAI or AWS's data centers in space anytime soon. So yeah, and then on the startup front, there's a few startups now, none of which have expressed sort of ambitions to build very large data centers yet. But a few of those are Axiom Space, Sophia Space, Madari in the UAE, a few others. Yeah.
Interesting. Well, yeah, let's hope you guys can position as the credibly neutral one for all the other people that don't yet have space arms. Yeah, I also want to ask, I kind of touched earlier, like some of the things that were peculiar to you that you learnt about like the space industry or operating in space, but like more broadly, what is one thing that you now know that you wish you did when you set out to found Starcloud? Yeah.
I honestly don't have a very good answer to that. It's just been like continuous learning, but it's nothing that I feel took too long to learn. Yeah, getting around, dealing with government, maybe we should have, is certainly an interesting and beast. It's a lot more relationshipy than had imagined. I'd imagined it was like, because they have a lot of application forms and things like this, which you can fill out. But unless you've socialized that with the people making the decisions informally, it's much harder to get contracts. So yeah, I think that'd probably be one of the main things.
Interesting. That's very cool. And I always like to ask, sort of in closing, what would you say is the most important or impactful book that you've ever read?
The one that comes to mind recently is the Elon biography by Walter Isaacson or Isaacman.
Okay.
Yeah, it's very inspiring. Elon in general is a very inspiring character to me.
Yeah, I'm excited to see where all of his endeavors go, but also love that book. It was a very cool read. And that's one thing, like when I was digging into even just the Starship forecasts and all the naysayers, it's like he's done this shit so many times. They've done like, you know, what is just completely beyond the bounds of plausibility. So yeah, fingers crossed. I hope it happens with Starship and the launch costs. Well, Philip, thank you so much for the time. Know you're a busy man. Really appreciate you coming on and wish you all the luck in the world with the November 2nd launch. And yeah, hopefully we can stay in touch. I'm very excited about what you guys are working on.
Thanks so much, Piers. Really appreciate it.